What about the future for Mars? Clearly, the big unanswered question is whether there is or ever has been life on Mars. That was not resolved by the Viking missions in the 1970s, and in fact the current Curiosity mission is not designed to detect life. Let's look back a little at the history. The Viking landers in the mid-1970s used 1960s technology and were incredibly impressive, but they could not do sophisticated biological sensing experiments. Basically, the landers dug into the few inches of topsoil, pulled those into the spacecraft, and did simple experiments to heat up the soil, look for what came off, or add nutrients to see if a metabolism was at work. While the results were generally either unconvincing or ambiguous, at least one of the experiments returned results that were consistent with the possibility of biological activity. And to this day, the PI, Gil Levin, of the Wolf Trap experiment, claims that his experiment may have detected life. Most scientists consider the Vikings not having detected life, but if you read the final report of the missions, the wording is surprisingly ambiguous. Clearly, we need to go back with more sophisticated experiments, designed 40 years later, and do the work again. An underlying problem or issue is the fact that life on Mars may not be like life on Earth. Its metabolism may operate differently. So if we look for purely photosynthetic or similar to Earth organism life, we may fail, not because it doesn't exist, but because we're looking for the wrong thing. That's a real concern. Meanwhile, we have free samples of Mars. There are close to 50 Martian meteorites that have been identified and cataloged. Most of these found on the pristine Antarctic ice, where meteorites sit in the top few inches of ice and are very noticeable because it's so white and uncontaminated by other objects. In 1995, there was a press conference at NASA headquarters where President Bill Clinton was president, where NASA announced evidence of possible life on Mars found in a Martian meteorite, the Allen Hills meteorite, ALH 84001. The evidence, however, turned out to be ambiguous. The most compelling piece of the evidence to the eye were images showing elongated forms deep within the rock that looked strikingly like terrestrial chains of bacteria, but on a much smaller scale. There was also geochemical evidence within the rock indicating metabolism at work. However, over time, and in the consensus of the planetary science community, the evidence was considered to be unconvincing because each part of it had alternative explanations that did not involve biology. In particular, the striking elongated forms could be produced by rock splatter when meteorites impact other rocks and the rock partially liquefies. We have about 50 free samples of Mars, Martian meteorites, most found in Antarctica, and we've analyzed many of them, but unfortunately most of these rocks are ancient and volcanic, so they've suffered enormous stresses and alterations over their history. Any life forms would be unlikely to leave traces in such rocks. It's essentially bad luck that none of the Martian meteorites are sedimentary rocks. If we ever go to Mars and bring back a rock, we'll head for a place where we think there was liquid water that used to be a sedimentary basin, and there we will have the best prospect of finding life forms laid down when Mars was warm and wet several billion years ago. Of course, if there's water on Mars now, it'll be underground, tens of meters underground in these subsurface aquifers that have been hypothesized. That is tantalizing, because no mission planned or existing can drill down that deep under the Martian crust to sample that water. We're left scratching around on the surface. Another problem with the Martian meteorites is we don't know their geological origin. It was enormous work to decide the one place the Curiosity rover would land out of 100 possible sites, and it was picked to be the best place where life might have existed in the past. The Martian meteorites tell us nothing about where they came from, and with no geological context for those rocks, they're of limited utility. The benefit of the rocks is that they can be scrutinized atom by atom, molecule by molecule in the lab, and that's something that can't be done with the rovers. Of course, if there is life on Mars, we may need some alternative strategies to find it.
Okay, everyone focus. Prepare to enter the atmosphere.
Okay, we have parachute online.
I have a picture right now. Okay, there's more to do. Now, if there is life, the Dutch will find it. Wait. What is he doing?
Now we wait.
Mars is the go-to target of the solar system. NASA's mantra is follow the water, and while there's not water on Mars now, we think there was in the distant past. The story told about Mars involves Mars that was warmer and wetter in the past, such that liquid bodies of water could exist on the surface under a thicker atmosphere. This is a compelling story. Unfortunately, it doesn't completely hang together. The best climate change and geological models of Mars suggest that it wasn't warm enough and the atmosphere wasn't dense enough 3 billion years ago to hold liquid water. Nobody knows if the climate models are correct or we just need more data to make them better. But it's a slightly awkward fly in the ointment for the story we'd like to tell about life on Mars in the distant past. Mars also has a bad reputation. NASA's deputy administrator once called it the death planet because so many missions had failed there. But if you actually look at the statistics, we've been doing pretty well with our missions to Mars and the inner solar system. The overall success rate for planetary probes in the inner solar system has improved impressively in the 50 years of the space program. In the 1960s, 2 out of 3 probes failed. That gradually increased to 2 out of 3 succeeding 10 or 20 years ago, and in the last decade the success rate is 90% or higher. Most of these are NASA missions, but it also includes missions by the Soviets and the European Space Agency. These enormously challenging technical missions are the pinnacle of achievement in engineering and technology, and they're now very successful. We routinely expect the Mars rovers to land, gather data, and send us back new information about the red planet. Sometimes, however, Mars does fight back. Looking ahead to the next decade, the clear hope is for a sample return mission. That would elevate the level of scientific scrutiny of Mars rocks far beyond what's capable with the rovers presently there. With a rock in the lab, we can analyze it in enormous detail, and if there was traces of microbial life from the distant past, we'd be able to find them. Mars missions have had some trouble lately because of the tough budgets in the European Union and the United States for space science. The ExoMars mission, for example, was cancelled. Mars sample return is now pushed off to about a decade from now, but most people think it will happen. The cost is substantial. Mars sample return will probably cost between $10 and $15 billion, and will have to be an international activity involving more than just the United States. The Mars landing missions are complex and have several parts to do the work efficiently and within a tough cost cap. Typically, there will be one mission sent to release an orbiter around Mars from which a lander will go. The lander will release a small rover that will fetch rocks, aiming at a particular site where the most high likelihood of life might be. That rover will then deliver the rocks to a caching station. A second lander will release a much smaller fetch rover that will bring them to a launch site where the rocks can be taken to Mars orbit to be brought back by the orbiter. It sounds complicated, but if it's all added up, the costs, risks, and benefits, this is the most efficient way to bring back Mars samples with relatively small pieces of hardware. If we imagine all the missions that are being planned or thought of for the next decade, Mars actually may get quite crowded. The final frontier in Mars is human exploration. Going back to President George W. Bush, the idea has been out there that we would use the Moon and Mars as way stations on the way out into the solar system. But realism and tough budgets have set in, and manned missions to Mars are currently off the table. They're also costed at nothing less than $50 billion, far beyond NASA's means at the moment. Meanwhile, the private sector has stepped in. There's a plan been announced for a one-way mission to Mars, involving someone either with a terminal illness or someone willing to take that risk and dedicate their life to the mission, that would cost substantially less than $50 billion. It's unclear at the present whether governments or the private sector will step into the gap and produce the first manned mission to Mars. Beyond the technical challenges, the human challenges of such a mission are enormous. The minimum time would be about 400 days, and most missions would last 500 or 600 days, nearly 2 years. The toll on the human body of such a mission would be enormous. It's not possible to launch a massive enough mission to shield the human body from the radiation of deep space, so there would be very high mutation rates caused by cosmic rays and high-energy particles. Even if it wasn't a one-way mission, astronauts on the way to Mars would take enormous physical risks. The psychological landscape is also equally uncertain. People have been in Earth orbit and have set duration records close to 2 years, but nobody has been so far from the home planet, and so far from recovery. Because if a manned Mars mission is sent, it won't be possible to rescue them if something goes wrong on the surface. The frontier for future exploration of Mars is the discovery of life. People imagine Mars was warmer and wetter in the past, and there may be evidence of ancient microbes. Perhaps there's life right now in subsurface aquifers. Current missions are incapable of testing for life. To do better, we'll almost certainly have to bring back a rock. This can be done robotically with missions that are planned in the next decade, or at vastly more cost and danger by astronauts. Manned missions to Mars are going to cost between $50 and $100 billion, and nobody knows who will be able to afford that or if it'll even happen within our lifetimes.